Dear students, welcome to the tutorial number 5. Today we will talk about not about software, but about the algorithms. We will look at classification and discuss and try the classification trees algorithm, and we will look at the clustering and talk about k-means algorithm. It's important to note that, first of all, today during the tutorial, I'm gonna use Excel worksheet, and its role is the calculator. So I do all the calculations here in the Excel worksheet. For you, if you prepare yourself to exam, it's not critical that you learn by heart all these formulas that I use in Excel itself, um, because on the exam you are asked to make one iteration of the algorithm or calculate something, but you can do it in any way which is comfortable for you on the sheet of paper in Excel as well, or you can use some other calculator. So in this tutorial, Excel, it's my calculator tool. And a second important thing, what people often ask is that, so to start and finish one algorithm, like classification tree algorithm, do it from the beginning to the end, it takes quite a lot of time. So on the exam, you will not be asked to do one algorithm completely from the beginning to the end. You will be asked something like do one iteration and say what you got, or what this outcome of algorithm means, or if you have some criteria equal to this, what should you do, and so on. So you will be asked one part of the algorithm or the understanding of this algorithm, of any algorithm that we discuss. On the next tutorial, we will discuss one more algorithm and model evaluation. I will have some theory in the tutorial. This theory is taken almost directly from the lecture, and I included here so that you have some context and you understand generally what we do. But all the details, please look them in the lecture. And the first slide here, it's like overall map of the data mining. And so data mining is kind of intellectual activity of human beings. It can be divided into two sub processes. It's discovery and verification. Discovery, it's kind of activity when we prepare the model that we will use in the future, when we discover some relations between the data. And verification, it's when we take this model and we see how good it works for in practice for some other data sets, right? Today we don't talk about verification. It will be discussed on the next tutorial. And discovery itself, it um, consists of two processes: prediction or description. The names are quite self-explanatory. So prediction, it's a kind of data mining when we want to predict something. Like if you have some sales for the last 5 years, and you know sales of ice cream, and you know that these sales, they depend on the temperature, then the question can be, what will be your sales in June if the temperature in June will be 20 degrees? So you predict something. And in the description, it's more like you describe the data that you have at hand. Often, data mining, it is used as a synonym for machine learning. Machine learning today, it's a very popular term. And in machine learning, in this tutorial, we'll consider machine learning and data mining as synonyms, even so you can find many different opinions. And in machine learning, this prediction part, it's called supervised machine learning, and description part, it's called unsupervised machine learning. And for us, unsupervised machine learning, it's the same as description, and supervised machine learning, it's prediction. And then in prediction itself, we'll talk today about prediction, actually, and about clustering as well. So in prediction itself, there are two kinds of tasks. It's regression and classification. What is regression? Regression, it's basically what I told now about the ice cream. When we have some input information, like temperature in June, and we want to predict the variable, but and this variable, it has a continuous, it is a continuous variable. Like sales, it can be 1,000, 1,500, million, and so on. Yes, this is regression. Classification, it's the same as regression, but here we want to the variables that we want to predict, it's not continuous, it's some categorical variable, or it's a binary variable. Binary variable means yes or no. Like you can find some examples for yes or no, or it can be categorical variable. Like we have information about many customers. New customer comes to us, and we are asked whether this customer will stay with our company or will not stay with our company. This will be classification. And about description, we will discuss it slightly later. Now, on this slide, I just wanted to show you how normally the data for data mining is represented. And it's represented or can be imagined as a table. You see, it's like some table. It can come from Excel, from your database, or from anywhere. And this is the example of some data about the customers, right? So about every customer, we know age of the customer, gender, number of complaints, and can be some other information about the customer. And every this column which we have in the table, it is column, but we can call it attribute, or if we talk about data mining, we can call it as a variable. And this is the input data, so it's something what we already know. And then so we collected this historical data about the customers, and what else we know here about the customer, it's whether customer stays with our company or not. So customer defect, it means that if it has value, yes, it means that this customer with these characteristics, this customer left our company. And when we see here no, it means that this customer stayed with our company. And so why do we generally need this data mining? Imagine that we have information about some other customer. So we know age, gender, and so on about the customer, but we don't know whether this customer will stay or will not stay with our company. And it might be useful for the business that we predict this value. So we know everything which is stored in these columns about the customer, but we want to predict the value of this red column. And this red column, that therefore it's called dependent variable. It's called dependent because we assume that somehow whether customer stays or not in our company depends on his characteristics or her characteristics. And characteristics are stored in these columns, which are called independent variable. So in general, our task is to collect the information about our customers that we have now, historical information. Then we evaluate like which factors really impact whether the customer stays with the company or not. And when we evaluated these relations, we can predict it for any new customers that we have. And that's why it's called predictive data mining. And in this specific example, we see that it will be the classification. Why it's classification? Because the independent variables that we try to predict, it's binary. So it's not continuous variable. It's not something like income or sales and so on. It would be a regression if, for example, the things that we wanted to predict would be like sales of this customer. We are asked what do you think will be our sales from these customers? Then it would be regression. And now the important characteristics of classification is that dependent variable is discrete, and independent variables, they can be discrete or continuous. In regression, we have only one difference, that dependent variable is continuous. And here it's also nice to note that we can represent this data from the table, our records, as the graphically. So I will explain a little bit how exactly we represent it, but I hope it's quite clear even without explanation. So every dot here on this figure, it's the record. Record, it can be anything. Let's now talk about the customer. So every this dot, it is the customer. So it corresponds to one row in this table. On this figure, we have then two axes. Horizontal one, which is called average order volume, and axis Y, which is called number of purchases in last year. And these two axes, they correspond to the independent variables from the table. Like we have here 3 dots, so probably average order volume would go somewhere later in the attributes, or also it's called features, in the features of the records. So since it's like two-dimensional representation, we have here only two attributes included. Let's now, for example, look at this customer. We see that we don't have here the scale, but he has one of the highest average order volume. So his order volume is 2, or like, let's say if it were 1,000, then order of this point or customer would be something like 600 euro, right? And then on this axis, again, we can see that this customer, he made one of the highest amount of purchases in the last year, and his amount of purchases is much higher than what this customer did. So that's how we represent the data graphically. Important also to understand that all these customers, they represented with two different sort of figures. They can be green circle or red square. And whether customer is represented as circle or square depends what value of dependent variable he or she has. So all the customers that defect, they are here red squares, and which stay with other company are represented as the green circles. And this is the historical data. Now, when we go back to the task of data mining, the question is, okay, when we have some information about some other customer, we talk here about only two attributes. Let's assume that information about these two attributes of some another customer. We ask the customer about this information, or we calculate it by ourselves from the database, and then we see that our customer end up in this graphical representation somewhere here. And then we are asked, okay, so what do you think? Will this customer will be green circle or red square? And even now, if we look at this data, we say, all right, in this area, almost all customers are red squares. That's why most probably this customer will be a red square. If our customer would end up here graphically, we see that, okay, here almost all the customers, they're green circles, so probably this customer will not defect. He will be red circle. And now let's look how exactly we do these areas. We provide these areas. So how does it look, let's say, from the point of view of computer of the algorithm? We see that what we did here, first step, we represented all the data graphically, but then we subdivided all the, so to say, root node or all the customers into two subcategories. And we did it by drawing this yellow line. And this yellow line, what exactly it is? It just divides the customers according to the number of purchases which they did in the last year. So if here, let's assume here is 6 purchases, then in the first subgroup, we have all the customers that have 6 or less purchases. And in the top group, we have subgroup or subnode. We have all the customers that have more than 6 purchases. Now let's concentrate on this bottom subgroup. We see, all right, in this subgroup, we have still quite mixed, there are squares and circles, so it's quite mixed data. Maybe we can subdivide again this all customers so that we define this area even better and somehow define the area where for sure we will get only defected or not defected customers. And for this reason, we build this yellow line. You see this yellow line, it subdivides the subgroup again. And if, so this yellow line, we draw it somewhere where, let's assume average order volume is 400 euro. And then when we subdivide it, so this subgroup again, we see that we get two very neat areas. And in every area, we have only defected or not defected customers. That's why when we have new customer who ends up, let's say here, we can ask him, or not ask, but take this data from the database or whatever. First, we ask, okay, do you have number of purchases less than, what was it, 600 euro? He answers us yes. And then we look, all right, and do you have average order volume under 400 euro? And he says yes. And then we will know that graphically he ends up in this area. And what this means for us, that the value of his or her dependent variable, most probably, according to our historical data, will be defected, red square. Now, it was very nice to do it here, but what if we have not two attributes, but what we have like many different attributes? So the question is, which exact questions should we, so to say, ask to our customers or not to our data? So by which exact attribute should we subdivide our data first? So here we subdivided first by number of purchases in last year, but we could do the same by, and we could start from average order volume. Yes, and then the question is like, which this threshold should we choose? And yes, so we need to do something like in the classification approach. Before we do this classification, our main problem is how do we actually prepare this questionnaire for our data, so to say. Now, if we look at this questionnaire in a bit another representation, we see that why this algorithm of classification is called classification tree. Because here on the illustration, we see that first we ask customers about their salary. They answer yes, no. When I say ask customers, we don't need to physically ask them. I mean, we can subdivide our data according to this attribute. And then when we subdivided everyone who has salary under 6, if I look at this illustration, everyone who has salary not under 6, it will be here. And we see that there we get only the records of the same category, of the same class. Therefore, I get here, it's called subnode, where I have completely pure data and I don't need to ask any more questions. So if someone comes to me and says that she has salary over 6, I assume that she will be in the class of green circle. But then when I look at everyone who answered yes, so who has salary under 6, there I have mixed results. So I need to ask some other question, and in this case it's LCR. Whatever it means, it's not so important for us. It's some attributes, and we again subdivide all our records, and then we get quite pure data. So our task is how exactly we develop this questionnaire, which attributes we include, and in which order we ask these questions. Because first we could subdivide according to LCR and then according to the salary. And I have one more illustration. So we decide exactly by which attribute we subdivide from the point of our branching objective. And branching objective, well, it's written here, we want to increase purity of the data, and we want to avoid splits that apply too few examples. So let's imagine that we are given all these records, and we can divide them according to 3 attributes. First one, it's salary, another one, it's LCR, and another one, third one, some other attributes, like their age. When we divide by the attribute, first attribute, we get these subnodes, right? Here people answered yes, here they answered no. I see that here in every subnode I get considerable amount of the records, but data is quite mixed. So it means that asking this question for these records, maybe it makes not so much sense. I don't get any interesting outcome. Then if I look at this attribute, when I divide according to this attribute, I see that, okay, in one of the subnodes, I get quite pure data. And for this subnode, I could ask some other questions more. But the problem here is that there are only 3 points. So we have split that has too few examples. Therefore, this division is also not optimal for us. And when I use some third attribute to divide the data records, here I got 2 subnodes. In every subnode, I have more or less pure records, and every subnode has quite pure data. So among these 3 options, which are what by which attribute I divide the node, I would choose this one. Yes, graphically. And then I would take every of the subnode and maybe ask some more question for this subnode. Some more would divide this subnode by some attributes. And in this way, I would build questionnaire tree, which looks like this. And when I build this a questionnaire tree for the known data, then I would ask or apply the same tree to the new data, and I could predict whether, in this case, customer is good or bad. Now some terminology. So root node. Root node is what we start from, and it is all the records that are available to us. So these are all these records, or this everything stored in this table. It's initial point what we start dividing. Then splitter or branching node, it's basically the attributes according to which we split the root node. You see here it's salary, but to decide, as I said before, what will be the next attribute, we need to try division by all the attributes and choose one which works the best for us. Then internal node, it's here it's yes or no. These are all records that end up in yes or end up in no according to their answer or to the value of the records in the to the value of the independent variable. So if I look here, this is the root node, and then I have internal nodes, this one or this one, because in each of these nodes they answered some question or they have the different values for the attribute. And then leaf node, it's basically the last node. It's bad, good, and so on. These are ones that for which I don't do any more divisions. And in that node, the records which end up there should more or less satisfy my assumption about data purity. Now, how do we really build this questionnaire? To build this questionnaire, it is the iterational process. Iterational process means that we do the same things multiple times until we get the results that we need. And every iteration in this process has several steps. So first step, it's find the most important variable. which is used for the division. So this step is basically what we do here. We somehow divide the node which we have by different attributes, and among all these attributes we choose the one which works the best. Then we split the tree according to this attribute. So we chose, for example, here this attribute and split the tree in 2 subnodes, or it can be more subnodes, but today we'll talk about binary data. 2 subnodes, and then we repeat the same steps. So we come back to the number 1 for every node. So basically, every of this node, they start to be something like a root node. We again apply here, choose all the attributes that can be used, use here all the attributes that can be used, and do it again and again before we come to the leaf nodes. Therefore, during all this process, we need to answer 2 questions: how to split a node, so split and rule, or how do we choose the best attribute? What is the mathematical approach to choose the best attribute? And then when do we stop? Stop and rule, splitting. Stop and rule you can check in the lecture. We will not talk about it too much, because today we will get the pure data, I guess, as a result. But sometimes you might stop earlier. Like, even so you see here data is not completely pure, you might say, okay, it's quite enough to stop branching at these nodes and don't do anything more. And now the splitting rule. We use it basically to evaluate which criterion use as the next. We'll see at the exact numbers or more precise calculations in the exercise in a few minutes, but now let's look at it from the more general perspective. So here is the example in which we want to decide according to which attribute we want to subdivide the root node. So here is the formula of information gain. This is a formula of how exactly we can calculate the information gain, information impurity. But now we will see which values we put in the information gain. And I will just make some example from my head as for now. So here, this is this node on the top. It's always the same node. It's a root node, because we see on 3 alternatives how we can subdivide it. So let's say that it's node n. Then we subdivide it in this case by some attribute. Assume that it's age, and we divide it by 2 another nodes, n1 and n2, like whether your age is under 30 or over 30. Here again and here again we subdivide by something. Let's say here we subdivide by income, if your income is under or over 3,000 euros, something like that. And then we get here node 3, node 4, and here node 5, node 6. Now, how do we now calculate the information gain? What is this IN? IN, we will talk exactly how we calculate it a bit later, but it is IN for the node n. Node n is here this one, the root node. So we would calculate impurity for the root node. Let's just assume for now that we calculated it and it's 0.97. Now we see next goes minus in this formula, minus, and then Pn1. Pn1, it is the proportion of elements in n1, in node n1, so exactly it's here, which end up in n1, and proportion from all the elements in the parent node n. Let's assume that in the parent node we have 100 elements, and in node 1 we have 60 elements. So this proportion, it will be 60 divided by 100. And we multiply it on the impurity, but now not for node, a root node, so not for the parent node, but for this node n1. Let's assume that this impurity, when we calculated it, it's 0.91. And the same we would do for the node n2. So it's minus. if in this node N1 we have 60 elements, here we will have 40. So it will be 40 divided by 100. And we must again calculate the impurity for node N2. And let's assume it's 0.42. And then when we calculate this all, we would get information gain, which we have when we divide by attribute age. The same we would do, the same calculation we will do for income. So we would change values, some values here, and let's assume we will still have here in the same node 100 elements, of course, so it doesn't change. But let's assume that here we have 10 and here we have 90 elements. So it means that impurity of the root node in the same node, it will not change. This number will be the same. But then we will update this number. It is the number of elements in the node, not N1, but now N3. It will be 90. Here will be 10. And here impurity will also be something different for this node. And again, we will get information gain when we divide by income. And then we will calculate the information gain when we divide by the last, some third attribute. And we will take a division by that attribute, which gives us the highest information gain. And now, how do we really calculate the impurities, this IN of root node or all subnodes? For that, we have three approaches. There are formulas for these approaches. Let's look at the entropy. If you will understand how entropy is calculated, others are calculated, use a bit different operations, but use this also letters P and so on. So this is the entropy, and what does it basically mean? It means that we need to find the sum for every j. Every j is the class in the node. So let's look at the node n, root node. We have there two classes, squares and circles. So we will first calculate this part for first class j1, and then for the second class j2. Now, how we will calculate it? Let's first calculate it for the first class when j is equal to 1. What does this mean? P, C, J, N, and so on. This is the proportion of elements of class 1 among all the elements in that node. So we can assume that if in this node we have 100 elements, and then of the first class of squares we have 20 elements, something like this, and on the second class circles we have 80 elements. Right? How do we calculate it for the class 1, which has a quantity of elements 20? We calculate it as 20 divided by total number of elements by 100. We calculated this, and now we calculate the multiplied by the logarithm with base 2 of the same thing. It was the first element, or calculation for the first class, for the j equals to 1. Then we have representatives of one more class in this node. It's the second class, and again we calculate the same thing for that class. It will be 80 divided by 100 multiplied by logarithm, but now 80, slightly another thing. Right, so we find j equals to 1, here j equals to 2, and you see here it's the sum with minus, so we can find the sum of these two elements and then multiply by -1, or we can just at the very beginning take them as negatives. And that's how we calculate entropy for node n. For node n1 or for any other node, we will do the same. For example, if in node 1 we have n1 is 40 and 2 equals 20, for example. Then to calculate this entropy for this node, we see the total amount is not 60, but it's not 100, but it's 60. So we would take here 60, here 60, here 60, here 60, and then first class has 40, and second 20. So this would be a calculation of entropy for the node 1, and you do the same for any other node. And here we are asked to build this classification tree. We will use Classif tree draft Excel workbook as a starting point. As I said, I will use it only as a calculator for my convenience. And then we are asked to use entropy as a splitting criterion. It means that we will, for every decision, we will use this formula, information gain. We will choose the split with the highest information gain, but information impurity itself will be calculated using entropy. So let's look at the data. Here is the draft, right? So these are all records that we have, the same as now we had in the slides. Every row, it's related to some customer, and our dependent variable is this. It's called class bias computer. So it's basically the discrete binary variable which says whether a customer with this characteristics purchase the computer. And then when we have some new customer who comes to us, we want to prepare the questionnaire in the form of the tree that we will know, that will help us to predict whether this customer will buy the computer or not. So what we basically want to start with. I will first organize a little bit here the worksheet. So I will simply copy it from the solutions. So now we will perform the first iteration. And for the root node and for all the subnodes that I get from different splits, I want to calculate various characteristics. So let's first calculate the characteristics for the parent node. And the parent node, it's basically the root node. It includes all the records that we have. And on the illustration that we have, this is the root node with all the records that we have. Now, first, what I have here in the first column, I want to calculate the number of elements of every class in that node, which is root node. So count class yes. So this is our dependent variable, and I want to calculate how many representatives of yes are in this node. And if I calculate them, it will be, I can use formula, and I guess in solutions you have a formula, but here I can just calculate it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 elements. Then of class no, I can just see that we have total 14 customers or records, so obviously of class no will be 5. Total that we have, it is n. So total it is what I named here as n. Here in example it was 100, but it is here 14. And now, so this was quite easy. And now we want to calculate the information impurity for this node. According to the formula, I want to do the following. It's equal to the I do the same for every class. So let's look at the first class, which is yes, or which in my illustration was class with index 1. It's with negative sign, and then I calculate the proportion of elements in this node. I mean, I calculated it and I divided by the total number of elements. That's why it's here total. And I multiply it now with the logarithm, with the base 2. And for a logarithm for, again, this proportion. So in Excel, it will look like logarithm. Then I choose the argument it is for this. And then I say that it should be base 2. So Excel, it will calculate for me this logarithm, and we don't need to care about it so much. And so this will be the value for the first class. Let's see whether it works. I mean, it works, but it's not complete because now we need to do the same calculation for the second class stored in this node, root node. So again, I will just copy it. And here I will substitute B19 with C19, right? For the second class, it just will be another cell. And here I can also substitute with the second class. So this is the calculation of this proportion and logarithm for the first class. This is the calculation for the second class. And when I use these two elements with minuses, it will be negative sum. So I press the button. So what I calculated here, IN of the specific node, of which node of this parent node, I basically calculated this. It's impurity according to the entropy. I used this formula, and this formula was written in the example here. I just implemented it. Excel is calculating. So we know that IN of this node is equal to what? It's equal to 0.94, and I want to make it shorter. All right. I cannot calculate here information gain for the first root node and this proportion because this parent node, it doesn't have this root node, it doesn't have parent node. Now, what we do the next? We're still in the same iteration. Now we divide this node by different attributes. We have here 4 attributes. And we see which attribute works for us better. Let's start for the age. So I write here age. Now, what values of age do we have? We have youth, middle aged, and senior. So basically, if I go back to the illustration, and if can I do it with the mouse? No. Okay, now I have a pen. So if we look at this example and apply here what we want to do now, we want now to divide this root node according to the age. And age, it has 3 possible values. use middle age and senior. That's why in every we will get here not 2 nodes as in this example, but 3 nodes. Let's call them N1, N2, and N3. In every node, we will have some number of observations. I don't know what will it be. We'll see it now. Right. But then for these 3 subnodes, we can use the same formula. So we will, for every subnode, calculate this information gain for subnode N1, then information gain for the subnode N2, and then information gain for the node N3. So now let's calculate in the same way as we did for the parent node, the same characteristics for all the subnodes for use, middle age, and senior. So the total amount of records in use node will be 1, 2, 3, 4, 5. It will be 5. This corresponds in the illustration, if this is use, this n for the use will be 5. Then for middle age, it will be 4, and for senior, it will be 5. Now for every of these nodes, as we did for the parent node, we want to calculate the number of representatives for every class in that node. And we can do it manually, but I will use one trick in Excel. So I will substitute or represent this table, this array as as table. My table has headers. And now, if I want to see the number of representatives of class yes in use node, I can just here filter H column by use. This will be all the records in the use subnode, and there will be 2 representatives of class yes and 3 of class no. Now for middle age, it will be 4 and 0, and for senior it will be 3 and 2. I just know it from solutions that I have, but let's see, senior 3 and 2. Now we have these 3 subnodes. We know their characteristics. Again, first subnode, second subnode, third subnode. We know these characteristics for each of them, and now we want to calculate this information gain. And we do it basically the same as we did for the parent node or for root node. I can copy this formula here. Let's see whether everything looks correct. Yes. So first we look the proportion of elements of the first class in this node use, and then multiply it with the log of this proportion and base 2. And then for the second class, we have only 2 classes. Now I can just copy it down. The same calculation, it will show me the error now. And the error is shown because of mathematical speciality here. We can. So basically, because we cannot find the logarithm of 0. If you look here, here C22, it's equal to 0. So 0 divided by 4, it will be still 0. And it's mathematically not acceptable to find the logarithm from that. Therefore, we get here an error. And we could make here things more complicated and so on, but one of the solutions is just to, when we have such situation, we can get rid of the, so we don't need to take into account the class which has no representatives. So I can just delete this part of this formula. And it will be a 0, and it's correct. And why don't we need to take into account this class no? Because if you look at the formula of information entropy, this J, it means it iterates over all classes that are really present in the node. And here, in our example, no representatives of class no are present in middle age node. Why do we also get here 0? So this IN, it means impurity of data. How impure is data? And if in some node we have only representatives of one class, it means that we have completely pure data in that class, and that's why logically impurity is 0. So we could get this impurity even without making any mathematical calculations, because we see that data is purely pure, and therefore its impurity is 0. Now we want to calculate this now PIN for every of these nodes. And we want this PIN because our final aim is to calculate the information gain when we apply H criterion. And this information gain, it's calculated is impurity of the parent node, which is root node, and the proportion of elements in each subnode, which is P and I, multiplied by the impurity of that node. Impurity we calculated. Now we want to multiply this impurity by proportion of elements. And proportion of elements in the use, we know that in this node we have 5 elements. So it is, let's say, this cell divided by the total number of elements in the root parent node. Parent node is root node. It has 14 elements. We can write it just like this. Reference the cells. And then we multiply it by information impurity of that node. It is this. We calculated it. I will fix this D19 cell because I want to drag it down. So I will make it absolute reference. It's enough to do it for the row. Yes. And now I have this PIN calculation. I can drag it down. Let's see. Yes, it looks correct. So now when I calculated this part as well, one thing that is left, I will write it here, it's to calculate information gain. Let's go again back to the formula. This is the formula. So it's IN minus PIN for every node. So it's equal to the IN of the parent node, here it's root node, minus this thing, minus this thing, minus this thing. And I get 0.247. All right. It is the calculation for the H criterion for this column. Now we need to do exactly the same process for all other parameters or attributes: income, student, and credit rating. Let's do it. So for the income, we have here how many categories? High, medium, low. So we will have here the same 3 subnodes. Illustration. So we had here by age, and here we will have by income, division by income, and again we would get 3 subnodes. I will not draw it again because it's the same. So it's high, medium, and low. Then let's look at the total number of elements. So in income high, we have 4. So if in the subnode we have 4, everyone who has high income, then in medium we will have 6, and in a low we will have 4. And now in every subnode, how many representatives of each class will we have? So when income is high, we will have 2 and 2. Do I record it? Yes. It's 2 and 2. Oh. And of course, in total, it's 4. Then here will be four and 2, and in low will be 3 and 1. All right. Now we are ready to calculate information impurity of every node. I can simply copy this formula. Does it? Yes. All the calculations look valid. We get here 1 because it's the most impure data, so to say, that we have. We have the same amount of every class. So you cannot do it more impure. And I can simply drag this formula down. Here we don't have cases where data is completely pure, so we don't have these mathematical errors. Now I can then calculate PIN. Yes, it looks correct. So I drag it down. This is PIN. And when I did this all, again, I can calculate the information gain for the case when we use income as the splitting attribute, splitting rule, and it will be equal the same. Information impurity of the root node minus each of these things. Basically, I can now see here already for these two attributes that splitting by h is better. Why? Because it has higher information gain here. And when we do the same thing for all 4 criteria, we will choose one which has the highest information gain. Okay, I do the same for the student. For the student, we have yes or no. So here we will have 2 subnodes. Subnode with yes and subnode with no. Then in yes, I'm gonna have 7 elements. It's no, also 7 elements. Then in who are students, there will be 4 who purchased the computer and 1 who didn't, and in non-students will be 3 and 4. I again calculate the impurity for every node. Then I can copy this simply. And okay, I have all the elements to calculate the information gain. So it will be impurity of the root node minus impurity, weighted impurity of each of the nodes. And now for the credit rating. I will not write all these values. I hope you understood how you do it. So I will just copy the solution You can check formulas at home, but we do there everything exactly the same. Here, let's make it a little bit prettier. I can calculate also information gain now for credit rating. It will be impurity of the root node minus this, minus this. And now when we have the information gain calculated for every attribute, we had 4 attributes, we make a decision of splitting the root node based on that attribute that has the highest information gain. The highest information gain has attribute age. That's why we choose this. This is the highest information gain, which is related to age criterion or age attribute. Therefore, if I go back now to the illustration, I had one option to split it by age, another option to split it by what was income, then whether someone is student, and so on. But we see that the best split will be if we split by age. Right? Now what we do the next? When we split it by age, we have 3 nodes or sub-nodes. And then, since it's a repetitive process, one iteration is over, and we will repeat it for all the sub-nodes, or almost for all the sub-nodes. I will now copy this illustration. Here. So this is our current state. I copied from the solutions. So we had the root node. Then we tried different options. How can we split it? We decided to split it by age. And then the middle nodes or sub-nodes that we get are senior, which includes only that customers that have age equal to senior, middle age, and youth. If now I look at the middle age sub-node, so middle aged, I can just simply in this root node select only that records that are middle aged. So these are the elements. There are 4 elements of this node middle aged. And if I look here, I see that they all belong to one class. It's they all buy the computer. It means that for this node, it's over. I don't need to split this node anyhow more. And this case is similar to what we have here. When you get the completely pure node, we can stop splitting for that node. But let's look now at these 2 nodes. And they aren't completely pure because senior, it includes mixed classes, representative of every class, and youth also includes representatives of each class. That's why we now need to repeat the process which we done for root node. We repeat it for every of these nodes, for senior and youth. And we will start from node youth. In the solution, we do it for youth. We'll do it here the same. So I can write down here node youth. And now I want to copy here the same table as we had before for root node, but now for youth only. For that, the easiest way is for me to filter table by customers that are in age youth, and I can then simply copy these records here. So this is basically this node. And now I do exactly same operations, but now as my parent node, I consider not root node, but use node. So I can copy this thing, headers, I can even copy headers and parent node. Then here we have iteration 1. I will write down the iteration 2. And we decided to now to go to the use node. We are quite free what we do in the second iteration, use node on senior node. Then here parent node. Now parent node is this node, use. Here we calculate the number of elements. Total number of elements is obviously 5 with that node, not 14. And how many elements of class yes do we have? We have 2 and no 3. Information gain. We already have impurity. We already have formula for that. It's 971. And basically we had this formula before. It was here. We already calculated it. We calculated everything before for this node. And now, same as before, now we need to choose which attribute suits best for splitting. Since we already splitted our tree by age, here we now never consider this attribute in the future. Now we consider only that attribute that never been used. It's income, student, and credit rating. I will do now for income. In income, as before, so it's like we had here, it can be high, medium, and low. Now, so we calculate how many elements would be in high income subnode if you would divide this use node according to income. Let's again enter the table. So total number in high, it is, I can calculate it without filtering, it's 2. In medium it's 2, and in low it's 1. And then here the values will be 0, 2, 1, 1, 1, 0. Okay. Okay, now I want to calculate information impurity as we did before. I will just try to copy these big formulas. Yes, formulas copied correct. Again, here for the high, we have an error because we try to calculate logarithm for 0. And we see that in our in subnode high, there would be no representatives of class yes present. That's why I can delete this first element in the formula. And obviously it would be 0, we just know it. Then we have 0.5. Is it correct? It's not correct. Here we copied formula where we deleted before one element. So here we have representatives of both classes. That's why we need standard formula for 2 elements. Because I copied from income here and here in medium, or from here from age. We had only one element in this sum, so I need to fix it a little bit. And now we calculate it for low, but again we have here one class is not present. I will not change the formula, I just know that it will be 0. No impurity, completely pure data. And now let's copy the next column, PN, PIN. Here we need to, yes, here this reference will be wrong, obviously, because it should reference now the total of parent node, and parent node now it's not the root node, but it is the use node. So I will change this reference to 60, so everything is referenced correctly. Of course it's 0, then it's 40 and it's 0, and now I can calculate the information gain, which is calculated as information impurity of the root node minus this, minus this, minus this. This was a demonstration of how we do it for subnodes, and now I will copy here the results of the calculations. I will not now explain these calculations because they are basically the same for every. Yes, and here are the results when we split by student and by credit rating. And the same as in previous iteration, we choose that attribute or splitting by that attribute that has the highest information gain. And among them, I see that splitting by student will have the highest information gain. So I say that this node, I will split it by student attribute. Yes. Now we go back to the senior node. We will do it in third iteration. So it will be node senior. Again, which elements are in this senior node? It's quite easy. I go back to the root node and choose here senior and copy it. This is the node senior, this one, and I will do here exactly the same what I did for all the previous nodes. I don't include age in the list of optional or options because we did already split by it, but I include all the other attributes. So here is the result. And for node senior, I can make a summary that the best attribute will be credit rating to split by. Now let's have a look what happens if node use we split by student. We see that we will get two subnodes. In the first subnode, we will have only representatives of class yes. In the second subnode, we will have representatives of class no. It's node use. Node senior, again, if I split it by credit rating, in the first node, subnode excellent, representative only of one class. In the node fair, representative also only one class, class yes. Graphically, it will look as you see in the solutions. Let's do it like this. So it means that we will get all the subnodes that have pure information. And if they have a pure information, we see it also from impurity values, they all are zeros. It means that we can stop splitting here, whatever our stopping criterion is, and we are done with this tree. It means that to classify any new customer for whom we don't know this answer, so for whom we don't know whether customer buys or not computer, we'll have to do something like this questionnaire with the real customer or with the just database, records in database. First, we will check the age of the customer. After we check the age, if this customer's middle age, we know that most probably this customer's in the class yes, he purchased this computer or computer from us. If the customer is age youth, it's not enough to answer this whether he buy or not computer for sure. We need to see if that person is student. And students, they buy computers, non-students, young non-students don't buy computers most often. And then if we talk about the senior, we need to take into account not if the students or not, most probably it would be even funny, but what are their credit rating, and somehow people with fair credit rating, they purchase computers, and with good one, they don't. And we build this tree with the help of mathematical approach as we see here. And also it's nice that to see from here that sometimes you use data mining to find relations between the data that wouldn't be obvious for human being. Like here, credit rating, I would assume maybe people who have better credit rating, they are someone who buys a computer right away. Yes, this was step-by-step creation of the tree for the classification. As I said, on the exam, you will be asked part of this task, like to calculate something or to make decision based on the data provided to you. I mean, these calculations, but they are provided to you. And here we use Excel as a calculator. So if you will not understand some formulas here, even so they are quite simple, the most important thing that you understand these formulas. And at home you will have an exercise. So if we would talk about misclassification impurity and Gini impurity, you see here you use the same, almost the same like numbers, but you do slightly different things with them. For Gini impurity, you calculate for every noted as 1 minus this proportion of every class, of every J, and you take this proportion in squared proportion. And for misclassification impurities, 1 minus maximal proportion for every class. All right. And here you have one simplification for the calculation of logarithms. All right, this was everything about the classification trees.